Alright, here we have section 6.2, example 6.2.4. And here they want us to solve a recurrence relation. They want us to get a closed form. So they tell us xn plus 1 is 2xn minus yn minus 1, and yn plus 1 is minus xn plus 2yn plus 2. And in a lot of ways, this mimics the idea of differential equations, so it's really a similar concept going on here. They tell us that x0 equals 0 and y0 equals -1. And so to do this, we can take this part and write it as a matrix, and then the constants we can do as a matrix. And so we're going to say that xn plus 1, yn plus 1 is equal to 2, -1, -1, 2 times xn, yn, and then plus the matrix -1, 2. And so if we call that A and that B, we have that xn plus 1 as a vector is equal to ax n and then plus b. Okay, so we have that, and so if I start with x0 and so forth, right, we've got x1 is a x0 plus b, x2 is a x1 plus b, but since x1 is just above us there, we've got a times a x0 plus b and then plus b, and so this is equal to a squared x0, whoops, 0 down there, plus ab plus b, and we could write that as a squared x0 plus a plus I times b. So we have that, and then similarly, you get x3, we would do that same sort of substitution and so forth, and we would get a cubed x0 plus a squared plus a plus I all times b. And so by the time I get to x n, that's a to the n, x0 plus a n minus 1 plus a n minus 2 all the way down to a plus I all times b. Okay, and you could do that as a proof, an induction proof, but this is one of those cases where I think it's pretty clear, if you were writing this for someone else, I don't know that you need a proof on that. I think other mathematicians would agree, sure, that makes sense. There's not really anything to make it really difficult. Now, so let's see, for this system, this matrix, or actually this matrix problem, they say it is easy to verify that what a to the n is. Well, maybe. Let's take a look at it. We have A is this matrix 2, -1, -1, and 2. So let's find the eigenvalues of it. I just need the determinant of 2 minus lambda, -1, -1, and 2 minus lambda. So I get lambda minus 2 squared, and then minus 1. So that's lambda squared minus 4 lambda, and plus 4 minus 1. So that is our lambda squared minus 4 lambda equals 3. Equals plus 3. And if we set that equal to 0, we get our lambda equals 1 and lambda equals 3. Okay, so we got that, and I've got the book in front of me, so I'm going to look back. We've done this matrix already somewhere in this book. Oh, well, no, not exactly. Okay, so I need to find the eigenvectors. The matrix that we had done before had a positive 1 in those off-diagonal elements. So although we have the same eigenvalues, we won't have the same eigenvectors. So real quick, I need to do a couple row reductions. So I have 1 and -1, -1, and 1. Now it's pretty clear to me that this matrix, if I just add the top row to the bottom row, I'll get zeros, so I get that. And so I have that in this case, x equals y. Right, so I have x minus y equals 0 for if I am trying to solve the homogeneous case of this. So x equals y. So one vector, call this, so I'll go back here and call that lambda 1 and that lambda 2. So x1 is equal to 1, 1. That's a perfectly good thing to use there. And then let's try it with lambda 2. So again, it was 2 minus, so we'll get -1, -1, and -1, right? Yeah, and -1. And again, pretty simple to see. I'll get 0, and so we'll get x plus y equals 0, and for then our x2, I have, say, 1 and -1. So there are my eigenvectors, okay, which means I can make my P matrix here 1, 1, 1, -1. And that also means that I can write A as P d P transpose, and that is 1, 1, 1, -1. My eigenvalue is 1, 0, 0, 3 there, and the transpose, oh, that's symmetric, so 1, 1, 1, -1. So that's interesting in that case. Okay, so then what we know is a to the n is equal to 1, 1, 1, -1. 1 to the n, so that's easy enough. 3 to the n, and 1, 1, 1, -1, like that. So we're trying to verify, you know, what they end up saying, what a to the n looks like. And so I'm going to multiply this through, and the 1, 1 times 1, 0, I'll just get 1. And 1, negative 1 times 1, 0, I just get a 1. And then on the, we'll get a 3 to the n and a negative 3 to the n times 1, 1, 1, negative 1. And so this is then 1 plus 3 to the n and 1 minus 3 to the n. And 1 minus 3 to the n and 1 plus 3 to the n. Well, I may have to pause it for a moment because in the text they have a 1/2 out in front. So I kind of feel like something's missing here. I mean, otherwise I get it, what they have, but they have the 1/2. So I'm going to pause this. You won't really notice other than you see me pause it. But I am going to check on that to make sure everything's okay here. Okay, well, I'm back, and the textbook appears to be incorrect. So this is indeed a to the n here. There should not be a 1/2 out in front of it. But that means we could then also write this as, you know, so we have our a to the n. We could write it as the matrix 1, 1, 1, 1 plus 3 to the n times the matrix 1, negative 1, negative 1, 1. Okay, and that's all they were doing. They just had those divided by 2, but they should not be. So this is their u plus 3 to the n v. Okay, but no dividing by 2. So everything's just off by that factor of 1/2. Okay, so then they say, well, hence, this, if I take a to the n minus 1 plus all the way down to a plus I, that I get this other expression they have. So now let's look at that. You know, what did they do? Okay, so a to the n is just u plus 3n to the v. Okay, so that means that a to the n minus 1 is u plus 3 to the n minus 1 v. And then a to the n minus 2, so we get a plus u plus 3 to the n minus 2 v. And so on, oops, dot, dot, dot there, plus a, which we can just write as, let's see, can we write that as just u plus v? So if this is, if I did that right, minus 3, yeah, so a to the 0 would be a 2. I'm kind of not liking this at all. Let's see. right? If I, oh no, I don't want a to the 0, I want a to the 1, sorry. A to the 1 is 3, 4, yeah, a to the 1 is, that's too big. Okay, well, I might take back what I said about that 2. Let me pause again, and here's what I'm looking at is if we choose a to be 1, then we'll get this 3 here times this stuff, and we'll get a 4 and a 2 and a minus 2 and so forth. It'll be 2 times too big. So I agree with the dividing by 2. However, the technology I use with Sage gave me the same answer I have. So I'm just feeling like something got copied down wrong somewhere. So let me take another quick look. Okay, hopefully you can learn from my mistakes. I just realized I all of a sudden it hit me. When I made the P matrix here, I wasn't, I forgot to make it orthogonal, or in other words, unit vectors in here. So instead of 1, 1, that's not a unit vector. I needed to normalize these things to unit vectors. And so since both of these have a length of square root of 2, I needed to make those 1 over the square root of 2. My mistake, and I'm sorry I went so far without noticing it. But we get that, and so then when I do a P, D, P transpose like that, I end up with 2 of these square roots of 2, so we do get a 1/2 out in front, like that. And so then I will get a 1/2 there, and we'll get a 1/2 there, so good, the book is correct. And so then I do have a 1/2 and a 1/2. So it's just the constant that, you know, I had wrong. The same idea. Everything else is the same. This is still working the same way. But luckily, when you work through it, you can find your mistakes. And so plus, when we get down to the a, n equals 1, we get u over 2 plus v over 2, and then plus I. So again, I apologize for those, but it happens. And so we can get down to that, and let's see, so a to the 1, oh, I need my 3 there, almost messed that up. Oh wait, no, not on the last one, I don't. Okay, so sorry, try not to do that too much. Let's see, I think, do I have that right? If n equals 1, oh no, yeah, there is a 3 there, and then an I. Now, but they point out that I can be written as, let me just write this again. I can be written as, let's see, u over 2 plus 3 n minus 1 over 2v. You know, plus dot 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 down to this plus u over 2 plus 3v over 2, so that's a. But then I could be written as u over 2 plus v over 2. And if we go up here and check that, our u and v, so if I add this matrix here and that matrix there, I get a 2, 0, 0, 2, and then divide by 2, I get the identity. And so, yes, I agree with them. And then they just pull all the factors together. And so, how many terms had u over 2 in them? Well, all of them. And there were n terms here because I had the I term and then n minus 1 different powers of a. So this ends up being the n over 2u, and then plus, and now they use an identity, so they're summing. If you look at this, we have 1/2 and then times the sum, and it starts at 3 to the 0, so I equals 0 to n minus 1 of 3 to the I, and then all times v. Okay, so we have that sum, but that sum, that is a geometric series, and what we know is that geometric series adds up to be, if I have my r here being 3, let's see, let me write down our formula for a geometric series kind of over here. If I want to sum I equals 0 to n minus 1 of some r to the I, what we know is that that is 1 minus r to the n over 1 minus r. Okay, so our value of r is 3, and so we would get for ours 1 minus 3 to the n over 1 minus 3. Well, that's a negative 2 on the bottom, so I could rewrite that as 3 to the n minus 1 over 2. And so we have 3 to the n minus 1 over 2 times v, and that is n squared u plus 3 to the n minus 1 over 4v. Okay, and so that is what they get for that big sum. And so now, remember, okay, we had that our x sub n is equal to that whole big sum here, this, right? If we go back far enough, we can find it somewhere. Here we go. So we had that. So we had a to the n x0, and then the sum, all this sum here times b. And so we do our a to the n times x0. Okay, so a to the n, oops, got to come back here. A to the n was that, so u over 2 plus 3 to the n over 2 times v. Okay, that was all times x0. And then plus our thing up here, n over 2u plus 3 to the n minus 1 over 4v, and that was all times our y0, or x0, actually times our b, that was a b. I got to come back and find it. Yeah, okay. So, and actually, b should have a, I would have used a lowercase and put this line over it, so I won't go back and do that everywhere, but since it's a column vector, yeah, so that's b. And so those values of those two things, so I had u over 2 plus 3 to the n over 2v times 0, negative 1, that was our initial conditions there, plus n over 2u plus 3 to the n minus 1 over 4v. And that was times the vector negative 1, 2. Okay. And now I'll take their word for it that it simplifies to this. So, you know, I would have to add everything, do the matrix multiplications and simplify, but they say, oh, that simplifies to the answer 2n plus 1 minus 3 to the n over 4, and 2n minus 5 plus 3 to the n over 4. Like I say, I'll take their word for it on that. But there is our closed form solution of the recurrence relation. Okay, and what made that much easier was this diagonalization process so that we could get these powers of A just so much easier. Okay. Now then, they also have a remark. We'll toss in the remark here about the solution here, 6.2.1, and they say if a minus I to the negative 1 existed, okay, in other words, if the determinant of a minus I was not equal to 0, then they could have used, okay, or we could have used that sum. So the sum I equals 0 to n minus 1 of a to the I, where a to the 0 is the identity matrix. They said we could use that, that's a to the n minus I times a minus I inverse. Okay, so yes, that's very nice. Now, you know, how did that, you know, where did that come from? Well, that, let's forget about matrices for a minute. That just came from the idea that if I, you know, take something like a minus 1 times a to the n minus 1 plus a to the n minus 2 plus down to plus a plus 1, that product is a to the n minus 1. So a to the n minus 1 factors like that. And so if we'd had, you know, if we knew that, then we can just solve for, you know, according to this then, right? As long as a is not 1, then this is just real numbers, right? If a is not 1, then a to the n plus a to the n minus 2 plus all the way down to 1 is just equal to a to the n minus 1 divided by a minus 1. So in other words, multiply by its inverse. And so as long as that inverse exists, that would be fine. Now, you know, why doesn't that inverse exist? Good question, because they haven't given us that theorem about determinants. But here's the thing: is if if I take a matrix A, so if I have the determinant, if I want the determinant of A plus a some constant, we'll say k times I, it turns out that determinant is the determinant of A plus k. Okay, so that's a pretty nifty result. And so you see, if k is -1 and oh wait, do I want determinant of k to the, wait a minute, I don't think that's what I wanted to write. We may just scratch that out and end it there, and then we'll, yeah, I didn't want determinants, sorry. Actually, we'll just scratch it out, but then I'll mention what we wanted. Sorry, I wanted eigenvalues. Okay, so eigenvalues of A plus ki, get that better, that's equal to the eigenvalues of A. Okay, so we'll use lambda, so we'll do lambda1 minus k. Here's a set, and then lambda2 minus k, lambda3 minus k, all the way down to lambda n minus k. Okay, so in that case, you know, since that's the case, then what happened was one of the eigenvalues of A was 1, and they're saying, you know, we want to do and I should have used a plus here. I was thinking ahead to where we were going. That should be plus. So then if I'm looking at A minus I, in this case, k is equal to -1. And so one of the eigenvalues of A happens to be 0. Okay, so, or A minus I, gosh, sorry. One of the eigenvalues of A minus I then happens to be 0 because one of the eigenvalues of A was 1. Okay, so that made an eigenvalue 0, and as soon as one of the eigenvalues is 0, then we have a singular matrix. And so that is, their remark there is really deep, actually. I mean, they've got, you know, they just kind of say it in passing, but that remark 6.2.1 is really quite deep, where they say, oh yeah, well, we can't do this. Okay, we don't get to do that because one of the eigenvalues was 1. There's a lot to that. There's a lot to that statement, and it, you know, comes down to this idea: the eigenvalues of A plus a constant times the identity turn out to be the eigenvalues of A just shifted by that constant. Okay, so with that, we'll call it quits on this example and see if we can make some more videos.